This video is prepared based on official accident reports and witness testimonies. April 26, 1994. China Airlines Flight 140 approaches Nagoya Airport on a routine evening service from Taipei, carrying 271 souls into what becomes Japan's second deadliest aviation disaster. Captain Wang Lo-chi and First Officer Chuang Meng-jung command the Airbus A300-600R in clear weather conditions, but face a crisis that tests the dangerous intersection between human pilots and aircraft automation systems. What begins as a minor control input error transforms into catastrophic loss of control when automation and human intervention conflict. The crew's battle against their own aircraft's computer systems creates unsurvivable conditions. This is the story of how inadequate understanding of automated flight systems can turn routine operations into deadly encounters. The accident demonstrates that modern aviation requires pilots to be systems managers rather than just aircraft controllers. The tragedy exposes fundamental flaws in pilot training for automated aircraft and manufacturer communication about complex system interactions. China Airlines 140 becomes a watershed moment for automation awareness. Modern aviation emerges stronger from this disaster, with enhanced training protocols ensuring pilots understand when automation helps and when it becomes dangerous. The accident's legacy transforms how pilots interact with computerized flight management systems worldwide. Airbus A300-600R, registration B1816, represents advanced aviation technology with sophisticated automated flight systems. Delivered to China Airlines in February 1991. This 3-year-old aircraft features computerized flight management beyond traditional aircraft. The A300-600R incorporates dual autopilots, auto-throttle systems, and flight directors working in coordination through complex mode logic. These systems provide precise flight path control, but require thorough pilot understanding of operational parameters. The Takeoff Go-Around (TOGA) system automatically configures aircraft for missed approach procedures when activated. This safety feature increases thrust, engages climb modes, and adjusts flight control systems for safe climb away from airports. Captain Wang Lo-chi brings 8,340 total flight hours, including 1,350 hours on the A300. Though most of his experience involves conventional aircraft without advanced automation systems, his background emphasizes manual flying skills over systems management. First Officer Chuang Meng-jung. Both pilots complete required training on Airbus automation systems, though investigation later reveals gaps in understanding complex failure modes and human automation interaction scenarios. The evening flight carries 256 passengers and 15 crew members on the popular Taipei-Nagoya route, serving business travelers and tourists between Taiwan and Japan. Flight 140 represents routine international operations where crews rely heavily on automation for approach and landing procedures. Flight 140 departs Taipei at 16:53 local time, with Captain Wang as pilot flying and First Officer Chuang monitoring aircraft systems. The flight proceeds routinely across the East China Sea toward Japan. Weather conditions at Nagoya present ideal flying conditions with clear skies, light winds from 290 degrees at 6 knots and 20-kilometer visibility. No meteorological factors threaten the planned instrument approach. At 1947, the crew begins normal descent toward Nagoya Airport with both autopilots engaged along with auto-throttle systems. The automated approach mode tracks the instrument landing system for runway 34. Air traffic control clears Flight 140 for ILS approach at 20:7, with the crew configuring landing gear, flaps, and approach speeds according to standard procedures. All systems operate normally during initial approach phase. At 20:11:36, First Officer Chuang disengages both autopilots to fly the approach manually, while flight directors provide guidance commands. This transition represents standard procedure for final approach segments. The aircraft passes the outer marker at 20:12:19 and receives landing clearance from Nagoya Tower. Normal approach parameters continue with aircraft tracking the glide slope toward touchdown. At approximately 1,000 feet altitude during final approach, First Officer Chuang inadvertently contacts the TO/GA switches on the throttle levers, immediately activating the go-around mode. This accidental activation sets in motion a sequence of automated responses that overwhelm the crew's understanding and ability to maintain control during the critical approach phase. The accidental activation of takeoff go-around switches triggers immediate automated responses throughout the aircraft's flight management systems. Auto-throttle advances to go-around power setting, creating unexpected thrust increase. The TOZA mode commands climb attitude and configuration changes designed for missed approach procedures. However, the crew intends to continue the landing approach, creating conflict between automation and pilot intentions. First Officer Chuang attempts to counter the unwanted climb by applying forward pressure on the control yoke, pushing the aircraft nose down to maintain glide slope approach path. Unknown to the crew, the autopilot's go-around mode remains active despite manual control inputs. The flight management system continues commanding climb attitude through the trimmable horizontal stabilizer. The aircraft's automation interprets the pilot's forward yoke pressure as resistance to be overcome. The horizontal stabilizer trims progressively toward nose-up position to counteract manual inputs. This creates a dangerous out-of-trim condition where the elevator and stabilizer work against each other. The pilot requires increasing force to maintain approach attitude against automated trim commands. Captain Wang observes the unusual situation but initially allows First Officer Chuang to continue managing the approach. Traditional crew resource management delays captain intervention during the developing crisis. The aircraft maintains approach path temporarily through continuous forward yoke pressure, but growing trim imbalance creates increasingly unstable flight conditions that threaten controllability. Before continuing this critical automation analysis, please subscribe to Through the Pilot's Eyes for detailed examinations of human-machine interface challenges and modern cockpit management. Your support helps us research these vital technology lessons. Now back to Flight 140's developing crisis. As the approach continues, First Officer Chuang applies increasing forward yoke pressure to maintain glide slope against the automation's climb commands. The physical workload intensifies with each passing second. The trimmable horizontal stabilizer reaches -12.3 degrees nose-up position, creating tremendous opposing forces against the elevator's nose-down commands. This configuration exceeds normal flight operational parameters. At 510 feet altitude, Captain Wang recognizes the severity of the situation and takes control of the aircraft. However, the out-of-trim condition now requires extreme control inputs that challenge even experienced pilots. The captain immediately encounters the same control difficulties as First Officer Chuang but with greater urgency due to decreasing altitude. Manual control authority becomes progressively inadequate against automated trim. Unknown to both pilots, they need only disengage the TOGA mode to resolve the conflict. However, training deficiencies prevent recognition of the automation state, causing their control problems. The crew's tunnel vision focuses on manual control inputs rather than system management. Traditional training emphasizes flying skills over automation monitoring and mode awareness. Engine thrust fluctuates as crew members attempt throttle adjustments while auto-throttle system maintains go-around power settings. These competing inputs create additional instability. At 2015-11, Captain Wang calls out "Go lever" as thrust increases dramatically, indicating awareness of the TO/GA activation but uncertainty about corrective procedures. The aircraft begins climbing steeply as the TOGA mode overpowers manual control inputs. Engine power increases to maximum go-around thrust, while the crew fights to maintain approach descent. Angle of attack increases rapidly as the out-of-trim condition and high thrust create uncontrollable pitch-up tendency. The aircraft climbs through 500 and 730 feet, far above the intended approach path. At 2015-17, the ground proximity warning system activates glide slope warning, alerting the crew to dangerous deviation from approach path. However, control difficulties prevent immediate correction. The crew attempts to reduce power and push the nose down, but the automation continues commanding climb attitude. This human-automation conflict creates aerodynamic conditions approaching stall. At 2015-25, the stall warning sounds for approximately 2 seconds as angle of attack approaches critical limits. The aircraft's speed decreases rapidly during the uncontrolled climb. The Alpha Floor Protection System activates, automatically increasing thrust to prevent stall conditions. This automated response conflicts with crew attempts to reduce power and recover normal flight attitude. At 2015-31, the aircraft reaches maximum altitude and begins nose-down pitch as aerodynamic stall develops. The crew loses all effective control as the aircraft enters unrecoverable descent. Ground proximity warning sounds, terrain, at 2015-37, followed by continuous stall warnings until impact. The crew faces impossible recovery situation with all systems fighting their inputs. Flight 140 crashes at 2015-45 into the airport boundary area approximately 110 meters east-northeast of runway 34 centerline. The high-angle impact destroys the aircraft structure instantly. The Airbus A300 strikes the ground in a near-vertical attitude with tremendous force, disintegrating on contact. Impact occurs within the airport perimeter, but short of the runway threshold. Emergency services respond immediately to the crash site, finding aircraft wreckage scattered across an area 140 meters long and 60 meters wide. The destruction appears complete and unsurvivable. Rescue teams work frantically to search for survivors among the shattered fuselage sections. Initial reports indicate possible survivors, though the majority of occupants perish in the violent impact. 7 passengers initially survived the crash, all seated in rows 7 through 15 in the forward cabin section. Their survival represents miraculous escapes from otherwise total destruction. Within 10 days, 3 additional survivors succumbed to injuries, leaving only 7 long-term survivors from 271 people aboard. The survival rate demonstrates the catastrophic nature of high-angle ground impact. Post-crash fires remain minimal due to fuel tank rupture patterns and emergency response effectiveness. The lack of extensive fire improves survival prospects for those who survive initial impact forces. The crash occurs in clear weather conditions with excellent visibility, eliminating meteorological factors from the accident sequence. Perfect flying conditions emphasize human automation interface problems. Japan's Aircraft Accident Investigation Commission conducts comprehensive investigation, focusing on crew actions, automation behavior, and human-machine interface factors during the critical sequence. Flight data recorder analysis reveals the complete sequence of TOGA activation, automation responses, and crew control inputs. Electronic data provides precise timeline of system interactions and pilot actions. Cockpit voice recorder captures crew confusion and communication breakdown during the crisis. Recorded conversations demonstrate inadequate understanding of automation states and corrective procedures. Investigation determines that TOGA inadvertent activation triggers cascading automation responses that overwhelm crew understanding. The system operates as designed but conflicts with pilot intentions. Simulation studies confirm that proper TOGA disengagement would have resolved the crisis immediately. However, crew training never emphasized recognition and correction of inadvertent mode activation. The investigation reveals that Airbus Service Bulletin A300-600R could have prevented the accident by enabling autopilot disconnection under excessive control forces. China Airlines had not implemented this modification. Cost considerations and maintenance scheduling prevented installation of available safety modifications. The airline decided to implement changes only during routine maintenance rather than dedicated safety upgrades. Crew training received scrutiny for inadequate coverage of automation mode awareness and complex system interactions during non-normal situations. The investigation concludes that automation design and crew training must better address human-machine interface challenges in modern aircraft operations. The accident exposes fundamental gaps in pilot training for automated aircraft systems. Traditional training emphasizes manual flying skills while neglecting automation management and mode awareness. China Airlines training programs focus on normal operations and standard procedures but provide insufficient coverage of automation failures and inadvertent mode activation scenarios. Both pilots complete required Airbus training but lack comprehensive understanding of complex mode logic and system interactions during non-normal situations. Training emphasizes procedures over conceptual understanding. The investigation reveals that many pilots worldwide struggle with automation mode awareness and proper system management during challenging operational scenarios. Crew resource management training inadequately addresses automation management and coordination between pilots during system malfunctions. Traditional CRM focuses on interpersonal communication rather than human-machine interface. Simulator training scenarios rarely include inadvertent automation activation combined with approach operations. Training programs assume pilots will recognize and correct mode errors quickly. Flight manual documentation proves inadequate for explaining complex automation behavior and recovery procedures. Technical information focuses on normal operations rather than failure recognition. International aviation lacks standardized approaches to automation training and competency verification. Different airlines and aircraft types require varying levels of system understanding. The accident demonstrates that automation can become a threat to safety when pilots lack adequate training and understanding of system behavior during non-normal operations. Thank you for following this critical automation analysis with Through the Pilot's Eyes. Please subscribe for comprehensive examinations of human-machine interface challenges and modern cockpit management that prevent accidents. China Airlines 140 drives revolutionary changes in automation training worldwide. The tragedy demonstrates that modern pilots must be automation managers as well as aircraft controllers. Enhanced training programs now emphasize mode awareness, system state recognition, and proper automation management during both normal and emergency operations. Pilots learn when automation helps and when it threatens safety. Airbus implements mandatory modifications to prevent inadvertent TOGA conflicts through improved system design and clearer pilot procedures. Service bulletins become requirements rather than recommendations. International aviation authorities mandate comprehensive automation training covering complex system interactions and human-machine interface challenges in modern aircraft operations. Crew resource management evolves to include automation management and coordination between pilots and aircraft systems. Modern CRM addresses technology challenges alongside traditional interpersonal communication. Flight manual documentation improves to provide clearer explanations of automation behavior and recovery procedures. Technical information now emphasizes failure recognition and corrective action. The 264 victims of Flight 140 represent the human cost of inadequate automation training and system understanding. Their sacrifice drives fundamental improvements in how pilots interact with modern aircraft technology. Enhanced automation training ensures pilots understand that technology serves them rather than controlling them. Proper training creates partnership between human intelligence and computer precision. Modern aviation safety depends on pilots who can effectively manage automation while maintaining situational awareness and decision-making authority in all flight conditions.